Thanks everyone for coming. We're happy today to have Marcus Michelen from UIC. He's going to tell us about roots of random polynomials near the unit circle. Take it away,
Hey,
Marcus.
great. Yeah, thanks for the introduction, Jacob, and thanks for the invitation and for all of you guys for making it here. So yeah, today I'm going to talk to you guys about the roots of random polynomials, and in particular, talk about the behavior of roots very close to the unit circle. So really atypically close to the unit circle. Most of what I'm going to talk to you guys about today is joint work. It's fairly recent, from a few months ago, with Julian Sahasrabudhe, who's currently at Cambridge. So I also want to mention, I can see the chat and I can hear you. So feel free to interrupt me, by text or by yelling something out. I will, and I'm happy to answer questions in any manner that you're happy to ask them. So first, what is the random polynomial that we're going to be looking at? So we're going to deal with the case where you're just adding up IAD random variables times z to the k, from k equals 0 to n. So throughout, n is going to be a degree of the polynomial. Throughout the entire talk, we're going to think of these coefficients as IAD. So this is often called the cat's ensemble, because there's sort of other ensembles. We could maybe have different variances for these dudes or whatever. But we're thinking about these as these coefficients being sort of probabilistically flat. And throughout, they're always going to be mean zero and finite variance. And for the vast majority of the time, you can think about them as standard Gaussians. We're going to talk a little bit about the history for various different coefficients and maybe what behavior will depend on coefficients and what won't, but Gaussians are going to be good enough for the most time. So really the guiding question. So if I give you a random polynomial, what can you say about the roots? How do they typically behave? So rather than telling you an answer that comes in the form of a picture, let me maybe tell you a bit of a historical answer, sort of what questions were asked and answered first. So the first thing people thought about with these were the behavior of the number of real roots of a random polynomial. So it's a little goofy to say it, but even as far back as Waring, he pondered the number of real roots of a typical cubic. This is like the 1780s. So from a probability perspective, this is like nearly prehistoric. Right? He didn't prove anything or even state anything formally. He wrote down something along the lines of like, if you look at a typical cubic polynomial, like about 75% of them have no complex roots. They only have real roots. But really, the study of random polynomials began in earnest in the 30s with Bloch and Polya. So they considered when your coefficients are plus, minus 1, and 0, they let these be uniformly at random. And they showed then that the expected number of real zeros is upper bounded by root n. So they proved a lot of really great stuff in this paper. And random polynomials is sort of only one of the small aspects of this. They also proved a lot of deterministic facts about polynomials. So from there, Littlewood and Offord really improved this and showed that with high probability with various different coefficients, you have an upper bound of log squared and a lower bound of basically log. So this is obviously much better than root n. But in the middle of Littlewood and Offord, having this really lovely series here, and this is also the same series that gave us these small ball probabilities and the Littlewood-Offord problem. Katz really made a nice breakthrough on this, and he showed that if you look at when the coefficients are IAD standard Gaussians, you can write down an exact integral for the expected number of real roots. And you analyze this integral to death, you end up with getting that it's approximately 2 over pi log. So again, the way he did this was he wrote down an exact expression for the expected number of real roots and analyzed it in order to get this. We're going to come back to this exact expression later on. So after Katz showed this, right, people were sort of off to the races. The idea is, okay, this is true for Gaussian coefficients. And Katz in his original paper even said, it seems like this method probably works for a wide variety of coefficients. But it took him about 5 years between the first paper and his second paper on this to show the same thing when your coefficients are IAD between -1 and 1. So again, here it's continuous. So really the thing that was really key to his argument was that you have a distribution that's continuous with respect to Lebesgue measure. So after that, Erdős and Offord proved the equivalent asymptotic expression for plus minus 1 IAD, so IAD Rademachers. And then Stevens and Ibragimov and Maslova proved this in a very general setting. So certainly any reasonable mean zero coefficients are going to be enough to give you this expression too. Okay, so yeah, the moral of the story here is you have roughly log n many real roots. We maybe talk a little bit more about what else we can say about real roots before jumping on it. So you can look way beyond just this first expression. In a really fantastic paper by Edelman and Kostlin, they found just a huge series, the expected number of real roots. So after log n, you get a constant, and then you get powers of n. Maslov also showed that you get a central limit theorem for the number of real roots. So not only is it like log n, right, but you have the mean is exactly what I said before, and you have variance in the order of about square root. Maybe the last.
What the variance is?
What was that?
Sorry, could you just repeat what the variance is here?
I believe the variance is the square root of that, but I don't remember that fully offhand.
Okay.
Yeah, okay. Right. And then Dembo, Punin, Xiao, and Zaytouni found asymptotics. So probably you have like 5 real roots or 10 real roots or etc. For any fixed k, they found that probably you have only that number of them. So an adjacent question, which I'm going to talk about before I give you sort of the meat of what's happening for complex roots, is what happens in a similar case where you look at, instead of a polynomial and look for real roots, you look at a trigonometric polynomial. So if you take an IAD sum of cosines and sines, where coefficients of each are IAD, then quals, in the case of Gaussians, found an exact expression by very similar methods to cats. And you just, it's literally an equality here. So then you get that this is roughly some constant times n. Even before this, so you get the same asymptotic, provided you just look at the cosine of the sine. So additionally, it's fairly involved to show, but you can also show that there's a central limit theorem for the number of roots of a trigonometric polynomial. This was shown by Granville and Wigman in 2008, and this happens with linear variance in this case. I think it's worth mentioning that the central limit theorem is still open for non-Gaussian coefficients. And in fact, the constant for what the variance is was shown recently by Do, Win, and Win to depend on the coefficients. It is not the same as in the Gaussian case and let's say the Rademacher case. Okay, I spent quite a bit of time telling you about real roots, which I've told you is only logarithmically many roots. And we know there are n many roots, so what's happening for the rest of them? Right, so it's quite an old result now. Hammersley and also Sparrow and Schur showed that most of the roots of the polynomial are really close to the unit circle. So the picture looks something like this. This is what we get for n equals 120. So not only are they close to the unit circle, they're also approximately equidistributed. And I want to sort of have everyone here like stare at this picture and notice a couple of things. So one, most of the roots are close to the unit circle, but not literally all of them. There are a few stragglers, and those stragglers aren't just a result of me only looking at n equals 120. Those stragglers do sort of exist in the limit. So really, the technical statement is if you put, like, let's say, a point mass at each root of 1 over n, then the measure where you add all of that up is going to converge to the uniform measure on the unit circle. So another way of saying that is if I look within 1 over epsilon of the unit circle, the proportion of roots within 1 over epsilon of the unit circle is going to tend to 1.
I have to say, it looks like a feat of serious LaTeX prowess that there's a 0 in the same line as the text on the bottom there.
Oh, yeah, I did have to cheat, admittedly. You know, it's yeah. Well, thanks. So yeah, let me also.
Are you going to comment on the thing that's happening around -1, I guess, as well?
Yeah. So what I wanted to point out also, which Jacob's pointing out for me, we assumed our polynomial had real coefficients, and I generated this with coefficients. What's going to be going on, right, is I'm going to have symmetry in the upper and lower half plane. So if we look near -1, for instance, we got these two roots really close together. That's just because I have a root that has a very small imaginary part and its conjugate is there. So sort of everywhere, everything's reflected above and below. There's another property that's sort of going on here, which is that you can see there's some type of repulsion going on. Things are sort of more spread out than if I had just thrown them in totally randomly. Right? There aren't a huge number of roots that are really clustering together. That's having this effect of really spreading things out nice and evenly. So lots of stuff is really embedded in this picture, but really the story here is most of them are close to the unit circle, and there's some type of repulsion going on. All right, so let's, oh, and I guess worth mentioning here, you might be able to notice, I think this guy has two real roots. There's one close to 1 and one close to -1. Okay, but let's continue. This is a really robust behavior. This happens provided your coefficients have like a logarithmically known. Is there some sort of negative dependence? Ah, yes, they will. So yeah, Jonathan is maybe stealing the thunder of what's going to happen in a few slides, but there is going to be a determinantal point process happening far away. And we'll see there is, in fact, some type of negative dependence. Yeah. Okay, great. So this is extremely robust behavior, right? If as long as you have a logarithmic moment, you're going to have this convergence to the unit circle. And in fact, pretty amazing, this is an if and only if. Yeah. So most roots are near the unit circle, but what's the scale? You know, everything I'm saying so far is just things are close, but I haven't told you how close. So Shep and Vanderby showed that most roots are happening on the scale of 1/n. So in other words, if I look on a band of, let's say, distance c/n from the unit circle, as c tends to infinity, I'm going to get almost all of my roots. So I actually found an exact expression in the case of Gaussian coefficients for the expected proportion within c/n of the unit circle. And really what they're doing is they're doing some type of complex version of what Katz did. In the case of Gaussian coefficients, you can find these exact integral expressions for expected numbers of roots. So here I'm going to approach Jonathan's question. So Perez and Virag, in a really just lovely paper, showed that if you look at roots macroscopically far away from the unit circle, you end up with a determinantal point process. And they have these two pictures next to each other, which are sort of like etched into my brain as just a fantastic picture of what's going on here. We have on the left a determinantal point process, and on the right a Poisson point process. So one symmetry that happens for these random polynomials that I want to point out is if I take z and I substitute in 1/z, this really just reverses the coefficients of my polynomial. So the behavior of roots within the unit disk is the same as the behavior outside the unit disk. So really what they identify is the limiting distribution of looking at k points within the unit disk. And here they end up with an exact determinantal point process when the coefficients are complex Gaussians. So really, this is like a miraculous thing. If you haven't seen a determinantal point process before, don't necessarily worry too much about that. But determinantal point processes are things that exhibit this type of repulsive behavior and have an extremely nice, algebraic form for sort of what the density looks like. If you ask, we're having k points at z1 through zk, more or less, the density is exactly the determinant of this really nice matrix. So this is.
Could I ask a question about the previous slide?
Oh yeah, please do.
You said that most of the points are in a band 1/n or constant over n. So how big a band would you need to take if you would want the number of points outside the band to be tight?
You would need it to be constant. You need it to be macroscopic.
Okay.
Yeah. So if you look outside, yeah. So in fact, maybe let me go to Perez Virag and let me just say, if you look at, let's say, the roots within the disk 1 minus epsilon, so of modulus 1 minus epsilon, as you take epsilon to 0, this random variable is going to approach a Gaussian. So you have a central limit theorem. If you replace the limits, so you let n equal plus infinity, so you look at this maybe infinite degree dude, and what you end up having is you look at the roots within a disk of radius 1 minus epsilon, then this guy, as epsilon goes to 0, is going to give us a Gaussian rescale. So you have to actually go macroscopically far for the unit circle to get something.
I see. Thanks.
Yeah. Any other questions on it? Yes, this is a really lovely result. And this is in the case of complex Gaussian coefficients, where you have a lot of really lovely, like conformally invariant tools you can use. And this is really an interesting paper because almost the entire paper is equalities and very few inequalities. It's really like identifying these really lovely combinatorial structures within this analytic function. So, you point out, this is not universal, and I'm going to argue it's maybe somewhat obviously not universal. So if I look at these complex Gaussians, right, this previous result by Perez and Varag says with positive probability, I can have a root just like way far out there. And in fact, I didn't have to sample too many. Like my computer did not get angry at me when I asked it to make this picture, and it found a root of modulus like basically 12. And now let's think about what would happen if I had Rademacher coefficients instead. So if I had Rademacher coefficients, right, deterministically, right, I would have all my roots are in this annulus between 2 and 1/2, right? So I would never have a root this far away. So the behavior of roots really far from the unit circle is going to depend quite a bit on the coefficients. In a lot of ways, I think this is maybe something natural to think about because it's going to depend a lot on the highest few coefficients or the lowest few coefficients, depending on where you look. Okay. So I'm talking to you about where most of the roots are. It's like on the order of 1/n, talking about what happens far away. Now the question is, how close is the closest root to the unit circle? So Shep and Vanderbeek conjectured that the distance is roughly on the order 1/n squared with high probability. Right, and now you could ask, what about the second root and the third root and so on? And they made a much stronger conjecture. They said if you rescale properly, you should get a Poisson process on the scale of n squared. So what this would more or less mean is you would sort of have, if you had this Poisson process type behavior, you would have that the roots close to the unit circle are maybe appearing somewhat independently of each other at a certain density. So now it's worth mentioning, shortly after Shep and Vanderbeek's paper, Ibragimov and Zaytouni, and also Konyagan and Schlag, in sort of two different generalities, showed that 1/n squared is really the best possible rate you could ask for conjecture one. And that says, if you look with an epsilon over n squared of the unit circle, with positive probability, you won't have a 0 in there. So this really is in some ways like a coarse thresholdy type thing. It's not going to be a sharp thing at a certain value. Okay. So the first thing I want to talk to you guys about is our main result here is that we prove both of these conjectures. So what you end up with is the closest root to the unit circle is roughly 1/n squared away. And in fact, right, if you look at the roots and you rescale properly, you're going to get a Poisson process of intensity 1/12. So another way of phrasing this, or maybe an easy corollary, right, is if I look at the distance for the closest root, then what you end up with, if I rescale by n squared, is an exponential random. Okay, so here's an artistic rendition from a very talented collaborator. If you look at the unit circle in this dark black line here, Perez and Varag is telling you what's happening sort of like way off in the distance, right? It's telling you that you get this really lovely determinantal structure in the case of complex Gaussian coefficients. Shep and Vanderbeek is saying most of the actions happening on the scale of 1/n, right? If I look on one of these bands, I'm going to get a huge chunk of my roots. And this chunk that I'm going to get is going to approach all of them, or 100% of them if I make the band big enough. And then our result is saying, while most of the roots are happening on a scale of 1/n, there are going to be a couple of guys appearing earlier. So we think about this as sort of three regimes here. We have Perez, Varag sort of telling you about maybe upper tails, Shep, Vanderbeek telling you about the bulk, and we're telling you about these exceptionally close points. Okay, so I spent a long time in the background, talking to you guys about real roots. So let's maybe bring the real roots back into the story here. Right, what's the distance of the closest real root to the unit circle? Well, in the same paper, Shep and Vanderby conjectured sort of the same thing for complex, just replacing 1 over n squared with 1 over n. They said that they expect the closest real root to the unit circle to be about 1 over n away. And if you rescale properly, you get a Poisson process. So indeed, they thought that it would be the case that you would have sort of the same behavior between real and complex roots, just on different scales. So we're also able to show that you do have a real root within 1 over n. This is the correct scale. But when you do this rescaling, you end up with a non-Poissonian. So I'll hopefully come back to this near the end. But what's going to end up happening is that you don't really have this independent behavior that you expect in a Poissonian limit. Okay, so before I really jump into anything, let me maybe summarize the results, and we can pause here for a moment. So our setting is we're looking at a random polynomial, degree n, i.e. Gaussian coefficients. The closest complex root to the unit circle is like 1 over n squared away. And if I rescale the modulus of these roots, I'm going to get like a Poisson process. And similarly, the closest real root is roughly 1 over n away. And now if I rescale this guy, I'm going to get a limiting process, but not a Poisson process. Okay, any questions on the results before I dive into some more about it?
So just to interpret this, you're saying it's really not, it's not like you're taking all the roots and then thinning them to get the real ones. That's not the right way to think about it. It's there's something honestly different going on with the real roots.
Yeah, so yeah, I guess yeah, there is something a little bit different going on. So I guess, you know, we can get back to it when the time is right, but I guess the vibe is we talked about how there's repulsion. If you have two roots close to the unit circle in complex world, they don't have to be close to each other. They could be extremely far from each other, but still close to the unit circle. But a really banal fact is if you're a real root close to the unit circle, you're either close to +1 or -1. So if I already know I've got one root close to +1 and let's say one root close to -1, those dudes are going to repel other possible real roots. That's why you don't have this Poissonian behavior. In complex world, you could have a root maybe like near the top of the unit circle and another one maybe further away, and these are macroscopically far, but still really close to the unit circle. So yeah, what's going on in real roots, sort of you don't have enough room to get this independent behavior.
Do you expect this non-Poissonian process also to be a determinantal process?
Oh, I don't believe so. Yeah. I think also, yeah, definitely do not expect it to be determinantal. You know, maybe I shouldn't say that as strongly. I would be surprised if it is. Yeah.
Okay.
Yeah, we could describe it as the zeros of some Gaussian process. But there might be some like magic you can do to show that it's determinantal in some kind of way, but not obvious to me. Okay. Oh, let's maybe get our hands a little bit dirty first. Let's talk about maybe the classic explanation for why roots are close to the unit circle for random polynomials. So now let's say I take a look at my random polynomial and I look at a point z that's macroscopically bigger than 1. Right, so now if I'm being super sloppy, right, I'm going to say that basically this looks like its highest term plus some smaller jump. Right, of course, maybe I might need the first few highest terms or maybe some logarithmically many or whatever it is, but more or less the highest terms are going to dominate. Right, and if the highest term dominates, right, this thing is not going to be 0 if z has modulus bigger than 1. And similarly, I can do the same argument for when modulus of z has less than 1. So this is going to roughly say what's happening here, right? If I look really far from the unit circle, like a really big modulus, the top term dominates. If I look really small, then I'm going to get the lowest term is going to dominate. And now, you know, this is all fast and loose. If you wanted to turn this into an actual proof, you have to turn to complex analysis. You can use the argument principle, or even better, integrate the Laplacian of log modulus f. These are two ways to compute the number of roots as an integral. And these will genuinely turn into proofs if you work hard enough. Where's the randomness coming in The randomness is saying that these smaller terms can't give you a massive coincidence to gang up on your biggest term, is why this randomness is going to come. Now, what I think is actually really interesting about this is technically a sketch of a proof that the real roots are close to the unit circle. Sorry, the roots are close to the unit circle. But in some ways, it's actually a proof saying you don't have any roots far away from the unit circle. And the fact that there are roots means you must have roots near the unit circle. So it would be nice if we had a heuristic to sort of explain that there are actually roots close to the unit circle without sort of having this extra thing of like, oh, there are n roots. None of them are far from the unit circle, thus they all have to be close to the unit circle. So let me present a maybe more combinatorial heuristic. So let's start with a really basic observation. A complex zero is just when the real part and imaginary part are both zero at the exact same time. Now, let's think about what happens looking at the real part on the unit circle. So I told you in the first few slides that this guy is going to have on the order of n many roots. And the same is true for the complex part, sorry, the imaginary part. So now let's see what happens. I look at the zeros of the real part of the unit circle, look at the zeros of the imaginary part of the unit circle. If I now, instead of looking at the circle of radius 1, look at the circle of radius r, where r is just slightly bigger than 1, all of these roots are going to wiggle a little bit. And now what we're hoping to have happen is maybe have one of these roots for the real part collide with one of the roots of the imaginary part. So now, with this sort of thing in mind, let's think fully in heuristic world. Let's imagine that instead of talking about roots of a polynomial, I just place n red balls and n blue balls uniformly at random on the circle. I'm going to think about these as the roots of the real and imaginary part, respectively. And now, a typical ball is like 1 over n away from a ball of the other color. Right? But a few of them are going to be on the order of 1 over n squared away. Right? If I look at, let's say, the number that are within c over n squared away from each other, right? I'm going to get some variable that's going to get larger and larger as c gets larger. And we get some Poissonian behavior. And now, if I move my circle a little bit, I think about the balls as wiggling around by on the order of h over n squared. So if I go from the circle of radius 1 to radius 1 plus h over n squared, I'm going to roughly move these balls around h over n squared. So presumably, some of them are going to collide if I choose h to be big enough. And now, since most of these balls are within 1 over n of each other, right? If I just like fully take this heuristic completely for granted, this will suggest that most pairs that collide will do so in constant 1 over n time. So this indeed is going to be the strategy we're going to use to show the existence of roots close to the unit circle and understand what they look like. So let me maybe draw a picture here. Again, the artistic capabilities of my collaborator are really showing off here. Right, if I look at the real and imaginary part, when I look really close to the unit circle, right, the zeros of the real and imaginary part are going to be roughly linear. They're going to roughly give us these lines here. So I think about having this like red and blue ball on the unit circle. And now when I think about moving my unit circle, I'm thinking about these roots as moving along these trajectories, sort of like with some velocity. And now as I'm moving this unit circle up, these two are going to collide into each other to give us a genuine complex zero at the point of intersection. Okay. Any questions on this picture or heuristic here?
So you also need to estimate showing that the derivatives are stable when you change the radius.
Oh yeah, lots of things like that have to be shown. Yeah, basically the mantra for a lot of this stuff is as long as you're not moving on the order of 1 over n, then things aren't going to change a huge amount. So if I'm moving on the order of like 1 over n squared, then this behavior is really going to be determined by. That's why it looks linear up to this scale of 1 over n squared. So yeah, obviously there are loads of reasons to maybe not believe this heuristic, and I'm going to dig into a couple of them in a moment, and we'll talk about how to deal with all of them. So obviously the most sketchy part of this heuristic is it's like not even plausible to believe right, that the roots are going to behave like uniformly distributed points. Right? In fact, that's really not the case. Right? On the left, we have zeros of the real and imaginary part of a random polynomial. And on the right, I've just placed the same number of red and blue balls. So now, again, let's notice a few things here. Right? Remember this theme. The zeros here repel each other. We can see that a lot on the left. In fact, there's also something a little more subtle going on. There's almost some type of interlacing going on, it seems. Whereas on the right, things are totally independent. I have some places where there are a huge number of roots, or sorry, a huge number of points, some stretches where there are no points at all. Really just things are not interacting. So it's not at all obvious that these two things are, that this is going to be a useful heuristic to have. The one thing I do want to mention, right, they're not going to behave randomly, uniformly at random. If you somehow did pretend that they would, you would still get some type of Poisson process, but the density of it would change. So the repulsion that's being exhibited on the left sort of changes the density of this Poisson process that we end up with, but it doesn't bite off the entirety of the n squared. It just eats into it. So a few more other small wrinkles, right? And this is maybe what Omer was suggesting here, is that, that the way that the zeros move depends on quite a bit about your polynomial here. And it's going to depend on the derivatives of the real and imaginary parts. Additionally, if we look really far away from unit circle, they're not going to behave in a nice fashion like this. Right? We need to have control over higher derivatives in certain types of ways. Because these are random polynomials, we can have these types of controls over higher derivatives and say that near the unit circle, you really are governed by just the first couple. It's not hugely important. In this picture I drew a couple slides back, the two lines are going towards each other. In fact, they always have to go towards each other or away from each other. They can never move in parallel. And this is exactly the Cauchy-Riemann equation. Again, all of these aspects here that I'm mentioning, if we sort of forgot that these things existed, you would still get a Poisson process on scale n squared, but the density would change. So all these little wrinkles are just sort of changing what this constant is by sort of just adding a little more flavor to what's happening on that scale. So how is the proof going to go? So it goes in two large chunks. One, I have to prove this heuristic is not snake oil, and that we're actually doing something here that's useful. And really what this is about is saying, forget about thinking in complex world. Let's reduce this entire problem to a question about the random trig polynomials on the unit circle. So we're replacing a 2D problem about the complex plane with a 1D problem just about the unit circle. And the next thing we have to do is just work really hard on the unit circle. And we're going to show convergence to a Poisson process using the method of moments. So we'll get into that when the time is right. But first I wanted to dig into this heuristic. Yeah, this is the general scale for how we show, how we understand the complex roots close to the circle. Let's dig into the heuristic even just vaguely, right? Why would you believe this is possibly true, right? Let's just Taylor expand the real part, right? And now this tilde right here, this approximate symbol, I've thrown away the second derivative and higher, right? If I'm not moving like too far, this isn't going to be a huge issue. And doing the same for the imaginary parts will tell us just where two zeros should collide. So the details here are really not important, but the moral of the story is, if I have a 0 of the real part at x and a 0 of the imaginary part at y, then there's going to be a complex 0 roughly at this quantity here. And I guess what I mean here is 1 plus this is what the modulus will be. So really the moral of the story, it's kind of irrelevant what this form is, but importantly, it's only depending on what's happening on the unit circle, not what's going on in complex. Okay, so now let's talk about, once we've reduced to the unit circle, how are we possibly going to show convergence to a Poisson process? So we're going to use the method of moments, which I want to just refresh quickly so we can get the general scale of like how you usually show convergence to a Poisson with moments. If you want to show a variable converges to a Poisson of mean lambda, it's enough to just show that these factorial moments converge to lambda to the k. And in fact, this is often really nice if xk is like a sum of a bunch of indicators, right? Then this factorial moment is adding up the expected number of like k disjointed, say k events that happen all at once. So you can do this if you want to show the sum of IAD Bernoulli lambda over n variables is Poisson in the limit. Maybe more combinatorially, if you look at the number of fixed points of random permutation, is going to be Poisson by this method. And even more generally, right, if you want to look at the number of cycles of, let's say, length k in a random permutation, you get something Poisson. So it's worth maybe just refreshing how maybe this last proof would go down to think about the obstacles to showing a method of moments for our complexes. Let's say that you want to show the number of cycles of length 2 in a random permutation is asymptotically Poisson. So the way I think about it is we have 3 things to show. One, you have to show that the mean is correct. Next, you have to show if you give me a whole bunch of disjoint pairs, the probability each of them gives me a cycle is going to, in the limit, be the same as what happens if they were independent. And maybe the last thing to show is you have to show if you have a bunch of pairs that overlap in some way, that the contribution from those is asymptotically negligible. So now, the same framework, which is basically how you show most kinds of convergence to Poisson by moments in the case we have some sort of dependence, is exactly what we do in our case. So we'll get there in a moment, but if you look at the number of complex zeros with modulus in a given set like this, we can write the kth factorial moment as some integral of some kernel. And we think about this as the continuous version of maybe summing over all k tuples in a discrete setting. And now we follow the same shape that most proofs by method of moments for Poisson give us. Right, we have to show that the mean is correct. We show that if I look at points really far apart, then you get basically independence. And we need to show the contribution from points that are not nearly independent is eventually negligible. So maybe I want to dig into this last point. Right, so I'm not going to get too deep in the weeds here, but in order to prove this last point, which is really the most technically difficult part of the whole process here, we have to show an anti-concentration result. So we show if you give us any arcs of the unit circle, and you ask for the real part to have zeros in each of the arcs, and the imaginary part to have zeros in each of those arcs, it's bounded above by a constant times n to the 2k times the product of the length of the arc. So again, the real and imaginary part have roughly n roots. So we expect the density to be on the order of like n to the 2k. And indeed, what this really shows is an upper bound on the joint density of having k zeros of the real part and k zeros of the imaginary part. And really, the difficult part in here is dealing with all the possible scales of when you have many of these arcs close to each other. Okay, so what is this integrand? Right, I've told you we can write factorial moments as an integral of some crazy thing. But what is this integrand? So let's maybe get into it a little bit quickly, because I think this is a super nice, just like general probability fact that I really love. So this is the Katz-Rice formula. It says if you give me a sufficiently nice Gaussian process, then I can compute the expected number of zeros in an interval as an exact integral here. So I alluded to this before, but this is exactly what Katz used in order to compute the expected number of real zeros of a random polynomial, and also what was computed by Dunnage, for instance, in order to show number of zeros of a trig poly. So proving this is kind of a pain, but I want to maybe argue that this is a pretty intuitive formula if we dig into what's happening here. So I want to give a quick sketch of this, because this will also help us explain the behavior of roots of random functions in general. So let's recall, this is what Katz-Rice is telling us. This is for G is just an arbitrary Gaussian process that's like reasonably nice. The linear expectation says just show it for really small intervals and then just add those all up. So we're going to show it for a really tiny interval and then just add up all of those tiny intervals. Okay, so now let's condition on the derivative and ask for the probability you have a zero. So now if you look at my amazing artistic capabilities here, right, you're going to have a 0, right, roughly if you shift, right, so you have a crossing between this. So if I'm taking delta really small, I can approximate g just by its like first Taylor polynomial. It's really governed by this first derivative. So this is going to happen basically when g is in this interval between 0 and let's say negative delta g prime. And now, since I've assumed g is a Gaussian process, I can more or less compute that probability, right? If delta is absurdly tiny, then what I'm going to end up with is I'm going to end up with this is basically delta g prime times the density at 0 of a Gaussian, which is just 1 over root 2 pi variance of g. Now just take the expectation, add them all up, and like cross your fingers and hold your nose that what you did was totally allowed. And if you do that, you end up with this exact thing. One thing I want to point out here is this tells us something a little bit extra than this really nice formula. It says that if g prime is really big, then I'm more likely to have a 0. Another way to say that is if I look at a place where I have a 0, then g prime is going to be larger than usual. And now let's think about what that's going to end up meaning, right? Katz-Rice is saying, if I look at a genuine 0 of g, then g prime is going to tend to be large. But let's think about what the mean value theorem says. If I look at two zeros close to each other, mean value theorem says that there's a 0 in between, and thus, sorry, the derivative in between. And that has to mean, if it's really close, that the derivative is small. But now these two things are really fighting with each other, right? Katz-Rice wants to force large derivatives at zeros. Mean value theorem says two close zeros gives you a small derivative. And the two of them together tell you that you shouldn't have too many zeros close to each other. And now, in this quick derivation of Katz-Rice that I showed you, the only place I used Gaussian was in this like last step of saying like, let's compute the probability g is in this small window. I used it to compute a small ball probability. But it can still be used to argue that at a 0, the derivative is larger than it would be otherwise. So, okay, this is sort of a very general phenomenon, not just for the types of random polynomials I spoke to you about before, but just a really nice general thing to keep in mind. Okay, so let's summarize the story for complex roots. Right, the first thing we do, right, we reduce the problem to the unit circle. We say instead of looking at complex roots, look at real part and imaginary part having zeros in the unit circle and colliding to give us zeros. Then we use the method of moments on the unit circle to get converged to a Poisson process. Right, and the vibe here, right, we just need to show that this factors when points are far enough apart, which says that the behavior on the unit circle is basically independent far enough away from each other, and also that it's uniformly bounded. And we put this together, you end up with convergence to a Poisson process. So one other thing I want to mention with this is we actually get a little bit more than that, right? Roughly, things are going to be rotationally equidistributed. So you can use what we've proven to show that you actually get a two-dimensional process. Just saying basically, if you look at these moduli, you can basically tag them with a random argument and you get the same thing. So they really are spread out randomly. So on the left, these points in red are plotted on the right after this transformation. Okay. Any questions on the complex roots before I sort of quickly describe to you the story of real roots? Okay. So actually, yeah, I have one more small thing I wanted to mention here, right? This really depended on the coefficients being Gaussian. But we suspect it's probably still true if you just have your coefficients are mean zero variance one. We think it's probably the case. We lose many of the tools we use, but there are very strong universality results for comparing the behavior of random polynomials on the unit circle in particular that give us sort of a lot of hope that this should be true. Okay, so let's maybe talk a little bit about how the story of real roots happens, and maybe why the story there is different than in complex roots. And I maybe mentioned this a little bit earlier to Jacob. But so let's remember what happens. The nearest real root is like 1 over n away from the unit circle. And if you look at the correct rescaling, so like look at the absolute value, subtract 1 and multiply by n, you get convergence to a non-Poissonian limit. And this we actually proved in the case of just mean zero variance one. And we'll end up seeing that you need way less info about the coefficients here. It's really a much more macroscopic thing. So why is it not Poisson? And I sort of, vomited all this math at Jacob earlier, but let's maybe talk through it in a more reasonable way now. Right, the roots repel each other. And in particular, if I have points within 1 over n of each other, then my polynomial is correlated at those 2 points. Right, and we have a really boring fact. A real root close to the unit circle has to be close to 1 or -1. There's no other way to be a real root and close to the unit circle. So if I know there's a root within 1 over n of 1, it's going to decrease the probability of there being another root. So there just isn't enough room for the roots to spread out and be far from each other, like in the complex root case. So, okay, how do we show convergence of any type of roots thing here? So a quick overview, right? All we do is we rescale our polynomial, and we show that this converges. So we're zooming in near 1 on a scale of 1 over n and renormalizing so things are macroscopic. And this is going to converge to a Gaussian process, which is effectively just the central limit theorem. With quite a bit more work, you can show that the point process of zeros of the polynomial converge in distribution to the zeros of the limiting Gaussian process. This handles the roots near 1. I can just do the same thing near -1 and show that these are asymptotically independent. So indeed, the behavior near 1 and -1 is going to be uncorrelated in the limit. It genuinely is this independent behavior. So how can I show that there are roots? Right, I have this limiting Gaussian process, and I think it was probably known who asked this question, I wasn't totally sure, asked whether or not we get a determinantal process. It's not totally obvious, but G has an explicit description. It's the zeros of this limiting G. So how do we show there's a root near 1? So I can rescale like I did in the slide before. This converges some Gaussian process. So the thing that's going on here is that when x and y are far apart, I'm getting that G is only weakly correlated on those. So now I just have to take a bunch of points that are reasonably far apart, and now I'm reasonably close to an uncorrelated Gaussian. And now, once I'm close to a mean zero, basically uncorrelated Gaussian, probably there's a sign change is going to be really high if I take a bunch of points. That's just exactly what we do. So convergence of Gn to G is going to then say I have a sign change of my polynomial with high probability. So the last bit I wanted to mention with real roots, right, is how would you literally show it's not Poissonian? So Katz-Rice basically says the probability you have zeros in these 2 intervals is roughly this density dx dy. Oops. A Poisson process is going to have this density factor. It's literally independent. And it's worth mentioning, actually, you can define these intensities for arbitrary k. And a Poisson process is defined by having all of these densities factored. So provided we show you don't have this independence, you don't have this density factoring, you're going to end up with a non-Poisson limit. So all we show is that this repulsion happens in this limiting setting. Right? So in other words, the probability I have 2 zeros at 1 basically is going to be really, really small. It's going to tend to 0. And this is going to say that the zeros do not form a Poisson process. So okay, very quickly, let me maybe summarize the story of real roots. We rescale to zoom in near 1. When I look at far away points, I get uncorrelated Gaussians in the limit. And that's going to tell us that we roughly have a sign change with high probability. With some work, we can show that the zeros of our polynomial converge in distribution to the zeros of the limit. And now we have some type of repulsion, and we're going to have this near 1 and -1, and so the limit will not be Poisson. Okay, so that's all I have for you today. I put our main results in the last slide, just in case there are any more questions. Thank you.
So people can unmute themselves and thank the speaker.
Thank you.
And if there are other questions,
Yeah, I had a question. So is this the same story with the real roots? Would it be the same story for, say, pure imaginary roots, or if you fix the argument?
So it's actually not. The real axis is really special. So if you give me any other ray, you're going to have, with probability 1, no zeros on that ray, provided our coefficients are, let's say, Gaussians. So really, the real axis is special because our coefficients are real. Everything else is sort of just sort of out in the bulk of complex stuff.
Right.
So I guess another thing worth mentioning, if our coefficients are complex Gaussians, you have no real roots with probability 1.
mhm.
So if you take go ahead.
For the complex case, the intensity of Poisson point process is just 1. Is that right?
Oh no, it's I think it was 1/12. Yeah.
1/12. Okay. So do you expect this number also to change for different distributions? So
Yeah. So basically no. For complex, it'll multiply by 2 only because you'll have the upper half plane and the lower half plane being independent, as opposed to being literally the same. But otherwise, we expect it to be the same. So we expect, as long as your coefficients are reasonable, and so maybe you give me an arbitrarily big moment, then I expect the same density there.
okay. Thank you.
I was going to ask, how far do you get if you replace polynomial by convergent random series?
Yeah, that's a good question. So obviously, if you add in some type of a tail, I guess it depends what the tail looks like, right? So if you look at an analytic function, this is the setting in which Perez and Varag look at the roots really far away. Then you can handle what's going on in a disk that's uniformly bounded away from the unit circle. So I guess the point is, the action around the unit circle, sort of these tails are going to really mess up what's happening. So you really do need to either think of a polynomial or add something small enough that it's effectively a polynomial. So sort of if you looked at, let's say, the Gaussian analytic function of j = 0 to infinity, with probability 1, the radius of convergence is going to be exactly 1. So you can't actually look beyond the unit circle or on the unit circle.
I see. Thanks.
Okay, so if there are no other questions, then we can thank Michael again, Marcus again, and we'll stop the recording. And we can have some